Okay, I think I can wake up everyone. Thanks for joining in such a large number for my talk on emulation and a little bit of open source infrastructure for testing promotion, the side. I'll try to keep the introductory part or the generic part a little bit less than I planned, I think. So we might also get some chances to dive into the details a bit more. Just a few facts about myself. I've been in the field for some years now. Originally pulled into the open source by the Yocto, and also since then I'm pretty passionate about everything that's related to embedded Yocto updates in particular. And yeah, in case you want to reach out to me, there are my contact details, but I'm also around the whole conference and happy to get in touch. For the talk, I'd ask you to gather all your questions for after the talk, just as usual, I would guess. For the outline, what I had in mind for today, besides the proof of concept that I came up with, I want to cover some like theoretical concepts or insights that I got while diving into the topic on my own. So that will be in the beginning a bit, and then dive into some code examples on my POC. And if we have time left after, we can also try to discuss some advanced topics. The whole thing is ongoing work, like a little disclaimer here. And while it's heavily based on actual project experience from real projects, I do not have like project-related code with me, just a POC on a Raspberry Pi level. But yeah, if you have any suggestions how to improve or feedback, then I'm happy to hear. So you might resemble some of these statements from your projects as well, especially the part when it comes to long waiting times for your test cycles or your builds are maybe something that you also had in your projects. The ones I have been engaged with had, for example, PR checks running from 45 minutes, not too bad, but still, if you have some iterations, kind of a hindering thing, up to 2 hours, including multiple pipelines and several boards to test. And this is like really tedious and will probably lead to features not completed on sprint end. These were due to, for one thing, test bench overload, so simply not enough hardware targets to run tests on, but also on the sheer number of tests and kind of a shotgun mentality. So let's just fire all the tests we have at every target on every PR. Yeah, well, then you're kind of having a bad developer experience by design. But also, the second point, the side effects were involved there. So if you have exclusive resources, such as, let's say, a CAN bus simulator running in your lab, and you only have one, and only one device can reasonably communicate with that, well, then all the others need to wait for that. And the last one is also one of my highlights, maintenance and debugging effort. I think I spent 2 or 3 weeks once to debug some weirdish behavior in a serial connection implementation, custom one. So that was no fun to get that running more or less stable. So how to tackle these speed and also accessibility issues that I observed? I had 2 ideas. One was, well, let's just use established frameworks for testing. That's also part of the side pitch I have with me today. And the other one was, well, there's this thing called emulation. Why can't we use that? So no pain if you use no hardware? Not really. Let's see. Before we dive into some considerations that I came across when thinking about this whole testing topic, I think the first thing you need to ask yourself is, what is my testing for? So in this talk, I will focus solely on this finding bugs case. and not about formal verification, for example, because that is a totally different thing to do. And for that, for example, in certain cases, you cannot avoid and should not avoid hardware, obviously. Then there is this question of what scope I'm going to test, or what am I talking about. I will be focusing on this thing that I call software system tests. So let's say you have a partition system with multiple software blobs involved, and you want to test the behavior between those. That's the case I'm talking about. For the others, for example, image tests with test image in Yocto or p-tests, there are other ways to approach that. Yeah, the obvious consideration is where to run your tests. And one thing I want to emphasize here is that I do not want to propose to only rely on emulation in whatever scenario, but that it's more like an addition to what you have, and that other environments might also come with interesting approaches how to alleviate the testing. And last but not least, and this was also kind of an aha moment for me, is what triggers a test. I mentioned that earlier. We had this PR check pipeline. This is one, but you can also think about other triggers like nightlies or weeklies or whatever you have. A release is probably also such a scenario. So emulation. Not all test scenarios are equally suited for running in emulation. That I can say already. There are some pre-designed ones. I mean, obviously, I have one with me that I think that is pre-designed for that, and that involves, as mentioned before, these partition systems or scenarios where reboots are involved, which cannot be that easily tested with, let's say, running a test image in Yocto. Or test cases or scenarios that involve putting the device in a very specific state and doing that deterministically, and yeah, basically getting rid of what has been done before. Then there are some that are less obvious, so that cannot be categorized directly to be feasible or not, and something like the aforementioned CAN simulation, for example, is one thing that I observed in my POC that might be feasible to do, but it's questionable like how much meaningful the results are if you run it like that, or they come with some extra effort in implementing in the emulated case. I mean, it would be nice to have something like a secured boot device emulated so that we do not brick real devices when also testing the bad scenarios. But yeah, maybe we can follow up on that later. It's not as easy to achieve as on the left side. Yes, and then there are some test scenarios that we can pretty much rule out from the start. Mostly if you have a software running that really depends on the hardware behavior or external stimuli, then it might be quite cumbersome to emulate those properly. I mean, in general, you need to ask yourself whether it's also economically reasonable to put in the effort to set up all the emulation stuff, or maybe extend it even to have a device that behaves close enough. I think if you're more on that left side, where oh, it's fine, I just want to have roughly the same behavior, and I'm focusing on, let's say, application level anyway, then it could be valuable for you. But if you're really trying to achieve that exact behavior of your hardware target, then you can hit a cost explosion pretty fast. What I would still like to emphasize here is this thing that I call high impact features. So it might still make sense for certain features, such as software updates, I would say, to, even if they impose some extra effort in the integration, that might be usable or feasible for emulation, because you're extend the breadth of your testing and can more easily scale out on that. I mean, in the end, you would still need the hardware involved for the final verification, but for example, to detecting errors in your behavior earlier, then it might be useful. Okay, now let's say we identified some use cases that are suitable for emulation, and we now want to integrate that in a developer-friendly way, let's say like that. And what my focus was is to achieve a way where you basically have to zero-touch the whole chain from building to testing, and have the tests executed rather transparently on either emulation or the hardware target. And this then would start with a dual machine approach. I think we had that in one of the presentations earlier this day. So you basically would add a virtual target, QEMU in my case, to aside from your actual product integration, and then by this have a single source of truth for your configuration. It can then also serve as a sanity check, especially if you want to experiment with certain features that are not yet available on hardware but can be emulated. So you would start with emulation then and can develop software already, and only later the hardware will follow. Yes, and last but not least, putting that in Yocto in your build configuration also allows to generate test environment configurations out of the box. The next part towards this way of having an end-to-end integration is where I would plug in the open source and would advocate for using open source components, and that's why Labgrid is there. I mean, Yocto I already mentioned, QEMU as well, and Labgrid is, in my view, a very potent testing infrastructure because it brings QEMU support out of the box and also plugs in quite nicely with a PyTest, which is also, at least in the projects I was in, somewhat common. In the end, you then automatically generate your build artifacts and test environments, which are then processed by the testing framework. And for the user or the developer running the tests is pretty transparent. And the framework even helps, Labgrid and PyTest can help you to automatically skip certain tests that are simply not feasible on either or platform. What I would like to emphasize here already is that the conscious selection of tests is, I think, one of the major levers I observed or I found while preparing the proof of concept, and is pretty much independent in the end of this emulation topic. Yeah, what can that bring? I mean, just a sneak peek, we'll look into the actual setup in a moment. In my not representative testing on Raspberry Pi and the emulation, the whole thing was able to speed up certain test scenarios, software updates in my case, by 4 to 5 times. So quite some gain. Okay, but where to begin? To have some first feeling of how the whole thing behaves, if that works all together and how much effort that is in regarding the integration, I decided to set up a somewhat representative setup with Yocto and quite a few development and build containers involved, and having an ARM target, because I would say it's still pretty dominant in the embedded space, even though I have, I think, 2 projects now that lately switched to Intel Apollo Lake and x86, but yeah, who knows? I'm staying with ARM for now, and that implements this A/B switching boot update flow that I mentioned earlier. Why software update? It's a bit interesting in regarding that there are several permutations of the software, and also it involves this partitioning and rebooting of the system. Yeah, and lately I was not. I was a bit selfish in the selection because there is already an existing example for that in MetaRauch community, so it was pretty easy to build up on that. So I have a Raspberry Pi 4 and my QEMU 64 to compare these two approaches. Okay, so let's dive into the code. To give you an impression how this system looks like, here is the system definition for the system image. The first thing I think that jumps into the eye is that there is no bootloader in there. And that is due to the fact that QEMU requires us passing the bootloader as a binary to the BIOS parameter if you want to boot anything else than a traditional x86 system. And that's also one of the breaking points for testing secured boot, for example, on that, because the ROM simply starts everything you give it. There are ways to extend that. You could introduce some sort of pre-bootloader so that you can put your actual bootloader on the disk. But yeah, whether it's worth the effort needs to be decided on a case basis. The next thing that you might see here is that the virt.io system, block file system, is used. So it's not a real eMMC, obviously, and QEMU is not able to directly emulate that, at least to my research. And the default would be to use such a virt.io block device. And this has some implications on how the kernel handles the whole thing, how the bootloader behaves, and also how the user space sees the device. In my case, I would argue that it's close enough, and that I'm focusing on the user space or application behavior anyway. So that abstraction provided by the kernel should be enough for my case. But you need to account for that. One thing that's also not in here is the bootloader environment. You need to store that somewhere. And the usual approach would be to have that on some sort of eMMC boot partition, for example. But that is as well not that easily to emulate. So I decided to just use the flash that comes with the standard emulation setup by QEMU and put it on there. Again, some deviations you see. But in the end, the boot flow looks pretty similar to something that you would expect on an actual target. What then comes next in terms of building the whole thing is the machine definition. Depending on your project, you might just use the default Poky ones, or you have the luck that there is an exact board representation in QEMU ready that you can use. Most often, I would say you will end up with defining something on your own, because it also provides some more control on what you pull in, or allows to extend it. In here, I have this CAN bus virtual already in there to run some tests that involve CAN bus. All in all, matching hardware really closely is pretty hard. So you definitely need to have that in mind when going that direction. Also, maybe one note, we will see that later, is by defining the QEMU boot variables here, not only for supporting run QEMU, but to have them included in the machine configuration also enables us to automatically generate the test configurations. The biggest other blocks besides the machine definitions are then changes to the bootloader behavior. In my case, it was the boot logic required to handle the virt.io. I just chose simple script approach, and you might even end up patching U-boot to support that. At least in scarce gap, it was required for me to fix some initialization issues in U-boot there. But yeah, we are all living upstream latest, right? Also, you can see here the boot environment image being prepared to be loaded as a Flash image. Yes, and beside the bootloader, kernel is an obvious part to account for. In this case, it was only this Flash configuration needed to interact with the bootloader environment, which is needed by the update framework. And the device tree, QEMU normally provides an on-the-fly device tree and simply passes that on to each of the stages. You can do that as well, but I decided to have that in the configuration repo, so static device tree, to also track changes better and have more control. That might come in handy also in secure boot scenarios, for example, if you need to pack all the things together and not having anything generated like on the fly. Okay, so as I said, we then generate the test environment configurations, and just a few hints on that one. As you can see there with the QB something variables that are the ones coming from the machine definitions, so you can have that single source of truth moment. And you can also see that we are leveraging the capability of Labgrid there, coming with an QEMU driver to spawn your instances already out of the box. So that was really convenient to set up, just provide some build artifacts to that, and then the framework does all the spin up the instant, close it down, and so on. The only thing that needed to be provided by the user or me is a strategy to control the boot flow or to put it in a specific state. But if you use common components such as U-boot as a bootloader, there are pretty good examples on that. So I set up the whole thing with almost no testing related infrastructure code involved. One just tiny detail I want to highlight here is this snapshot parameter. While searching for that, I came to the conclusion that QEMU documentation is like really, really big and lots of details in there, but it's sometimes a bit hard to find just the right fragment of knowledge that you need in that moment. And in this case, the snapshot parameter allows me to set up the instances that are spawned to be ephemeral, so no changes are persisted in the images that are provided in there. So you always start at a fresh, a clean state when starting that instances. And this is quite handy in terms of avoiding side effects between your test case executions. Yeah, okay, how does a test case look like then? That's just one example from the update tests I wrote, and there's no mention of a specific target in there. So where does that come from? The magic all happens in the PyTest fixtures provided to that test cases. So these update underscore something, that's where we inject all the environment specifics, and these come from the conf test. So in the end, you ask the framework, hey, in which environment am I running? Just give me the target. And because all these classes have a same, the shared API, it's basically independent on what target you chose. The test will execute on either ones. Still, you need to ensure that the logic can run on that target. And for that purpose, you can use PyTest tags or feature flags as provided by Labgrid to express on which targets the test can execute. Okay, so some numbers. That is my not representative test I run on the Raspberry Pi 4 and the QEMU ARM 64 instance. The Raspberry Pi, like on the one side of the spectrum, running everything in sequence. I mean, it was pretty close to my actual test host, just one line of Ethernet and a direct serial connection. Also not something that common if you have remote infrastructure, but still quite slower than running the whole thing in emulation and with full parallelization. That meaning, throwing as many processes as you can afford at it and running as many test cases in parallel as you can. In this case, it was only 5. Okay, so what are the takeaways from that POC? Speed gains are indeed possible, but some time is still, or sometimes we're still the same, and these mostly relate to just normal boot sequences. Reboot takes time and should take time because we want similar behavior in the end, right? So the speed gains mostly come from just running all the test cases in parallel. And the whole thing only works if your test cases are indeed independent of each other. I mean, obviously, if you want to have some state on the device, on the virtual device, that your next test case depends on, then you need to either manually set that up or choose a different way than the ephemeral instances. Relating this, how close are you compared to the actual hardware? One indicator can be to check out how many different build artifacts you have. So the reuse of build artifacts was pretty decent in my case, so only 14% differences, just package count. And these are mostly the different images and output artifacts. And I came pretty close already just by using the same architecture, obviously, and the same CPU. Yes, and I mentioned that already. One big lever also to reduce the overall time spent for your test suite is to select tests reasonably. Does it work for you? So if you are fine with going with the simple off-the-shelf scenarios, then probably yes. But if you want to go really on an exact match of your platform, like on the right side, then it's a totally different story. And it in particular pays off if you just use the modern, let's say, tool chain, because the components I showed earlier support QEMU out of the box. Actually, this is used quite widespread already in their own testing. And if your project phase matches to the expectations, especially in early project phases, I think that can be of great help. You won't save money and time if you spend it elsewhere. That's also obvious. So if that only leads to all the tests being executed now twice, then you're not better off. And I mean, there is definitely some barrier concerning the integration effort if you want to get close hardware matching. In my projects I mentioned earlier, I think especially this infrastructure load and the positive developer experience would have at least strong arguments to introduce that. I wasn't able to convince them yet. So coming to an end already, these are the main takeaways. I think whether it makes sense to consider emulation in your project depends on obviously the product. So if it's very complex or involves physical processes, slow running processes. I had one, I think, that needed to pump some water from A to B. I mean, then emulation is not the right thing, maybe, or simulation is needed. It also depends on which test scenarios you want to run on that emulated target, and in the end, whether it's technically and economically feasible to perform all the extra work and integration that virtual target, while still getting meaningful results on that. Yeah, the aha moment I had regarding the test selection is maybe very obvious, but for me it was not. And this where to execute what question is something that you can ask yourself regardless of the target you're executing your tests on. And my personal takeaway is that there are indeed some low-hanging fruit, I would say, but you can also fall into complexity pits quite fast, especially if you look into more advanced peripheral support or in itself complex use cases like secure boot. And that's it from my side already. And I would like to take your questions now. Okay.
So thank you for the talk, very interesting. While you were presenting, you basically showed the example of doing update tests. I was also thinking because we're doing similar things, and the real fun part of testing is the power of skewing an update. And I think when you're running in a VM, it's quite simple to just fill the VM and test a power site. Have you by any chance done anything like that already, or any experience with?
Okay, just to repeat the question shortly, it's about whether I have some experience with cutting the power. Meanwhile, I've not done that yet. There's this interesting topic I did not dive into this rabbit hole yet, which is called QMP, which is the protocol to control QEMU instances. That's also what Labgrid is using for spawning and controlling that. So you can also use that to put the device in a certain state to manipulate certain devices, introducing bit flips, for example. But unfortunately, I cannot say how much effort that is to go that direction. Killing processes should be rather easy.
Why did you go for QEMU instead of Raspberry Pi 3 machine in QEMU?
Yeah, because the question was why not choosing the existing board emulation for Raspberry Pi in the QEMU. That was because actually I started by implementing the virtual machine in a manner to represent more product-ready devices, and then ended up, well, I want to compare that to something. I have only a Raspberry Pi lying around, so that's why that is on my table.
For your driver and hardware problem, have you looked into using mocking?
Question was whether I looked into mocking for driver and hardware interfaces. What I did is I checked how hard it is to have a CAN bus simulation running, so at least a bit more towards the peripheral side, and I came across the point where the emulation would be fine, but it imposes extra effort or requirements on the test host. Because in the CAN case, you need to reasonably use that in your testing. You need to inject messages, for example, and read out messages. And QEMU offers only the binding to the vCAN, which then needs to be provided by your host, your test host. And if you want to parallelize thing, well, then you have this exclusive resource again. But I mean, especially if it's about specific peripherals, that would then require more work on the QEMU side, where there is a driver model or in general an object model, and you can check whether there is something suiting your actual hardware. I did not have like any idea what to test, but if it's not, you would then need to implement that on your own. And yeah, I would first ask my question whether the test would then give me that extra knowledge, insight, and if it's not, in the end, the little pain to just run it on hardware.
The Python test you showed, the Python code that was executing, was that the actual test, or was that like calling external things to be used? I'm not familiar with how that actually.
Yes, I can just roll back. this one, right? The question was whether this is the actual test. No, I mean, the actual meat is in the execute all steps, which is a custom fixture I created, which implements this deploy the image on the system, trigger the update, reboot, check whether everything is okay. But this one was implemented in a way which is transparent to the device again. So my for this to pay off, all the test logic that is executed in the end needs to be independent on the test. And I mean, that would be also my expectation, that my virtual target behaves more or less the same as the actual productive target. So time invest if the rest of the testing infrastructure is already close to that. So running PyTest, for example, and Labgrid. I learned a lot about QEMU along the way. So my time invest is not representative, but I would be courageous enough to say that it's rather a matter of 1 or 2 weeks for the setting up the build and configuration to create these artifacts, and then to provide a Labgrid environment configuration that actually performs the job. Best guess. No. Actually, I mean, in this comparison here, you can see that, for example, this just setting up everything, i.e. booting an instance or booting the target in a state where the test can start, has almost the same timestamp. Even QEMU is sometimes slower than the actual target. It depends on in what state the hardware target is. I had only one, so if that is stuck on a different version, I still need to employ the starting version first and before I can run. So that depends, but this was pretty much the same. But the main time difference really comes by, you can see there are 8 workers executing these 5 tests in parallel, while on the upper side I have the same 5 tests but run in sequence. I mean, you can still optimize in the above scenario by choosing a sensible sequence, obviously, if you want to test this going from that version to that version. But parallelization is the bigger lever. Yeah, and also cleanup. I mean, in my example here, there was no special state the device is in. But if you have other test cases, other suites that run that, I don't know, create some more user data on the device that you should erase before starting your test case to be clean, then this would require extra effort in the setup.
You said that connectivity tests are a problem. Is it possible to bind to the network interface from the host? So that you do tests to a real backend or maybe to a simulated backend server?
Yes, so Ethernet is pretty good supported. Actually, this one, I mean, you're on my test host, the interaction with the target was still running over Ethernet, right? So each instance of QEMU spawned a SSH port that the tests environment interacted with, and you can probably also put other members into that network and use that for testing as well. When it comes to more specific protocols like CAN, that's a different issue, because I think also the abilities to mimic or mock that on the host are more restricted than for the Ethernet use case. Okay. I have maybe one, because I worked so much for that, or am still in the process, just one extra bit. Secure boot, I mentioned that before. I'm still working on making that run on the emulated setup. What I can tell already is that it at most creates some partial validation for that. Again, with the target with the goal to just find bugs. But QEMU, as I said before, runs whatever you gives to it, so no first level bootloader verification, and it also misses some peripherals like replay protected memory to implement a proper secret handling and establishing the components that are involved in the secure boot. So you could, for example, from starting after the first bootloader, still check whether your fit image is properly verified and whether your DM-verity works. You can do that, but I mean, it's not a real root of trust that you're testing with.